Chapter 31, Faraday's Law. We have so far introduced the electric field and the magnetic field, and we learned that electric field can be created by electric charges, and a magnetic field on the other hand can be created by a moving electric charge or electric current. Now, do you wonder, is an electric charge the only way to create the electric field? And is a moving electric charge or electric current the only way to create a magnetic field? Are there other ways for us to generate electric field and a magnetic field? Are there any more connections between the E and B field? Well, it turns out that there certainly are, and the story of the connection between E and B field goes much deeper than what we have learned so far. As a matter of fact, if you introduce a time-varying E field and B field, okay, if we allow the electric field or the magnetic field to change over time, then we find that there are new ways to generate the electric field and the magnetic field. In fact, E field and B field can be generated from one another, believe it or not. E can generate B and B can generate E. So it's not just an electric charge or moving or electric current that can generate those E and B fields. There are other ways to do that, and with that understanding we'll find that the connection between E and B are much deeper than we thought before. So E and B are now going to become inseparable. They will be the two sides of the same coin. Okay, so we're going to start with our discussion about Faraday's law, which has to do with a time-varying magnetic field. Later on, we'll also look at what happens when the electric field changes over time. Now, we're going to start with a discussion about the concept of magnetic flux. This is similar to the concept of electric flux, which we started with the second chapter, Gauss's law, in which we have to calculate the electric flux. Now, when we calculate the electric flux for Gauss's law, we typically used a self-enclosed net, right? What's called a Gaussian surface. It's not an open patch or open area, rather it's a self-enclosed net. That was the expression for the electric flux in Gauss's law for electricity. Now, let's look at a magnetic flux. Okay, suppose we start with a certain area, and we can then, just like the case of the electric flux, we can define a direction of that area, which is to be perpendicular to the surface of that area, and we have this vector A, and then through that area there is a magnetic field B. The angle between A and B is theta. Now, how does one calculate the magnetic flux going through this area? Well, in general, the magnetic flux over a finite region can vary from place to place, and if that happens, I cannot simply use a certain uniform value of B to cover the entire area. Rather, I'm going to divide it into pieces. I'm going to divide this area into pieces, and each piece only has a small area or area element, which I call dA, and I can then find the magnetic flux over this tiny area, d phi b. Okay, as you know, the definition would be B dot dA, right? And if we integrate, we will get the magnetic flux over this entire area A, B dot dA, just as we would define the electric flux. Okay, now in the case of electric flux, we calculate the flux through a self-enclosed net, so we had a circle on it indicating it was a self-enclosed net. What happens if we do the same thing for a magnetic field? Okay, so then we will have something like this, right? A self-enclosed net. What would this be equal to? Well, if we follow the analogy between the electric and magnetic field, you know, in the case of electric field, that other side was equal to what? It was equal to the charge enclosed by the net divided by epsilon naught, right? If you follow the symmetry between E and B, you'll find that in our case, 1 over epsilon naught should be replaced with mu naught, and then what? The charge enclosed. Okay, what should I replace it with? Well, what is the equivalent to an electric charge? That would be a magnetic monopole, right? So I would have a magnetic monopole, but you know, there is no such thing as magnetic monopole. At least we haven't found one. The only source of magnetic field we have found so far was what? Electrical current, basically charges in motion. So you multiply this by 0. Okay, there is no magnetic monopole, and so you get 0. So if you try to find a magnetic flux through a self-enclosed Gaussian surface of any shape and size, you're always going to get zero. You're always going to get zero. Okay, this is a so-called Gauss's law for magnetism. So we're not going to be too concerned about the magnetic flux over the entire net. Rather, we're going to be concerned about the magnetic flux over an open area. Okay, it is not a self-enclosed net. So let's look at a just a patch of open area. So this is our definition for the magnetic flux. There is no circle on it. Okay, be careful about that. All right. What I want to discuss is what happens if that magnetic flux changes over time. Okay. Phi b is defined as b dot dA integration. So d phi b dt, that will be the rate of change of the flux, right? d dt of this integral. Now mathematically, how does one change the value of an integral? Well, there are two ways you can change the value of an integral. One is you can change the integrand, in this case b, right? You can change b, so b can change over time, right? That's one way to introduce a time varying integration, is to change the integrand. But the other way to do that is what? You can keep the integrand the same, but you can change what? You can change the range of integration, right? In other words, you can change the shape and size of the area over which you obtain the magnetic flux. So you see, there are two ways to do that. Again, one is to change b, the other is to move the area around. In other words, you want to move the border. You want to move the border of this patch. Okay, you move the border. Either way, you will find that there is a magnetic flux change over time. And what happens if there is a magnetic flux change? Well, this will be the subject of this chapter. It's called Faraday's law. It's named after Michael Faraday. That's how he got his name. Named after the electric capacitance. Remember Farad? Okay, that's named after Michael Faraday, who was a contemporary of the great James Clerk Maxwell. They worked together as partners. Together they had great discoveries about the theory and the experiment of electricity and magnetism. Now, what does Faraday's law say? Faraday's law tells us that as soon as there is a time varying magnetic flux, okay, I don't care whether it's due to the change in the B field itself or the change due to the change of the area, or it was the border of the area. Whatever happens that changes the magnetic flux, something results. And what is that? That is what's called an induced EMF. Induced EMF, epsilon. And with a negative sign here. Now let me explain to you what is the meaning of this EMF and what is the meaning of this negative sign. Okay, first of all, this is the so-called Faraday's law of induction. Okay, suppose here is an area that I'm concerned with. This area could be bordered with a real current carrying wire, or it could be just an imagined area with nothing. Okay, either way. And then over that area there is a magnetic field, so you can calculate the flux, right? Now if the flux doesn't change, nothing happens. Okay, but as soon as the flux changes, so there's a d phi b dt, then all of a sudden we say an induced electromotive force, or EMF, will result. And the meaning of this EMF is that it would have driven a real current should there be an actual wire surrounding the border of this region. Okay, and what is the direction of that EMF? What kind of current would it power? Well, here's the thing. Here's what this negative sign means. This EMF, if you give it to a real wire, if there were a real metal wire around it, it would have driven a current which flows in such a direction that that current itself would generate its own magnetic flux, which tends to cancel, okay, which tends to cancel the change in the original flux. Gee, you wonder what that means? Well, basically it means nature doesn't want to change the magnetic flux. It wants to maintain the flux, okay? For whatever reason, it does not like any change in the magnetic flux. So what if the flux does change? When the flux does change, nature tries to fight it off, and what it does is that it will generate an EMF around the perimeter. That EMF, it's like a virtual battery, okay? What would have done if there were an actual wire is that it would have driven a current, and the purpose of that current is to generate its own magnetic flux. Remember, current can generate a magnetic field and therefore magnetic flux, right? Would have generated its own magnetic flux, whose job is to erase the effect of the flux change. So if let's say if there's a flux like this, right, the way I draw it, it's out of this surface, and let's say the B field increases over time. Okay, let's say the B field increases over time. If that happens, what can you say about the flux? Is it changing? Of course it is. Is it increasing or decreasing over time? If B increases in magnitude, of course there will be an increase in the flux out of the paper, right, out of this surface, right? And then nature doesn't like that. So what does it do? Well, it will then automatically generate an EMF around it. And what's the purpose of that EMF? Well, we can determine the direction of EMF assuming that we had a wire. It doesn't have to have a wire, okay? But suppose we had a wire. Then a current would be induced, will start to flow in that wire. That is induced by the change in the flux. And the direction of the current is such that it will always generate its own flux, which tends to cancel that increase. See, you had a flux increase. Nature doesn't like that, so it wants to generate the flux. Is it into the paper, out of the paper? Well, the flux out of the paper is increasing, so in order to cancel that, you want a flux going in, right? You want a flux going in. And what kind of current would generate a flux, electromagnetic flux going in? Is it a clockwise current or counterclockwise current? Well, obviously that would be a counterclockwise current, right? Because a counterclockwise current, a clockwise current, right? A clockwise current like this would have generated its own magnetic field going in, and that is how you reduce the increase in magnetic flux. Nature wants to maintain that flux. It doesn't want to increase. Okay, so that will be the direction of that current should there be a wire here. And that current is powered by an EMF which is induced by the change in the magnetic flux. And that EMF, of course, would generate a clockwise flowing current. Okay, if there were no actual wire here, just vacuum, then of course there wouldn't be a real current, but there still would be an EMF in that place, so that once you had a wire here, a current would have been actually flowing in this sense. Okay, and of course, if that magnetic field is decreasing in magnitude, then what happens? Well, still, nature wants to maintain that flux, so you would then generate a current backwards, so that that current produces an outward magnetic flux, which tends to maintain the original flux, which was decreasing. Okay, so this is the idea of the Faraday's law of induction, and this is what also the negative sign. What does it mean? The negative sign means that the induced EMF always tends to cancel the change in the original magnetic flux. Okay, it always opposes any change in the original magnetic flux, and that's what this negative sign means. It's an opposition to the change in flux. Okay, that is the so-called Faraday's law of induction. And it doesn't matter whether the flux change again is due to the B field change itself, or is it due to the change in the shape and size of the surface, in other words, the motion of the border of that area. As a matter of fact, you can change the flux both ways, right? One is due to a change in B field, the other due to a change in motion of the border. And because of that, we divide the induced EMF into two categories. Okay, generally it's called induced EMF, no matter how the flux changes. But in general, we can divide it into two categories, depending on how the flux changes. Okay, the first type is just simply due to a change in the B field itself. Okay, that we usually just simply call it induced EMF, just like the general term. But if the change in flux is specifically due to the motion of the border, which changes the shape and size of the area, therefore changing the flux, then because there is motion involved in order to change that flux, we call that type of induced EMF motional EMF. Okay, motional means it's due to the motion of the border.